Welcome to Convergence of Fourier series. So before we get into Convergence of Fourier series, we'll get into sort of the required type of function. So definition, f is said to be piecewise smooth. On the closed interval AB if f and f prime are both continuous except at finitely many points in AB. And all left and right limits exist on A and B. So all left and right limits for both f and f prime exist on closed interval AB. Of course, for A, we're only looking at the right limit. For B, we're only looking at the left limit. But otherwise, all left and right limits exist. So we get a theorem which says that if f is piecewise smooth, on the interval, closed interval, negative L to L, then the Fourier series converges. On the entire interval, negative LL, and it actually converges everywhere. And we actually know precisely what it converges to. So, oops, I need to give myself a little more space. I apologize. All right, so the Fourier series converges everywhere, and f of x, this Fourier series, f of x is equal to our original lowercase f of x, if wherever f is continuous. On the open interval negative L to L. It is equal to the average of the left and right limits. So essentially, if we come at x from the left and we come at x from the right, and look at the left and right limits and then average them, this is wherever f is discontinuous on the open interval negative LL. And then last but not least is what happens on the L's. And then beyond that, we will get our periodic extension. So at negative L and L, we will do, we'll take the limit coming from the right at negative L and the limit coming from the left at positive L. So the left and right limits that exist at each of our boundaries. Take the average of those values. This is at x equal to L or negative L. And then finally, the function will just extend to your 2 pi periodic everywhere else. So beyond this, f is 2L periodic. So furthermore, we get that f of x plus 2L is equal to f of x. So we can, our Fourier series, because all of our sine and cosine n pi over Lx are all 2L periodic, the sum will be 2L periodic, and so our series will just be 2L periodic. So even though our original function f was just negative L to L, our Fourier series will just go forever. So we previously found the Fourier series for the function f of x equals 0 between -5 and 0, and 2 between 0 and 5. We found the Fourier series on -5, 5. But even without finding that Fourier series, we would know what this converges to. So essentially, our Fourier series f of x converges to f, except at discontinuities. In this case, the only discontinuity would be at x equals 0 and at the endpoints. Which will be x equaling -5 and 5. At those points, we split the difference. So I like to just sketch the original function. So let's first sketch f. The original f, our lowercase f. So from -5 to 0, we're just equal to 0. And then from 0 to 5, we're equal to 2. So sketching this function. We have the two horizontal lines, y equals 0 and y equals 2. Y equals 0 running from x equals -5 to 0, both closed circles. Then we have an open circle for our line y equals 2 at x equals 0, and then closed circle at x equals 5. So this is the original f. So our Fourier series we're going to change all those closed circles to open circles. We will make the function 2L periodic. And then once we do that, we will add closed circles in to like split the difference for each jump continuity. So again, redrawing my original function. I'm going to extend much further out now. So I'm going to go all the way out to 15 on the right and out to negative 15 on the left. This way I can show multiple periods of our Fourier series. Again, doing open circles. We'll go from -5, sorry, that's not what I wanted to do. We'll go from -5 to 0, running just right on the x-axis. Using open circles. We'll go from 0 to 5 up at y equals 2, again using open circles. So this is my step 1, if I number these. Then step 2, I apologize, let's update my screen again. Next step, you obviously do not need to draw these in multiple different graphs. I just want to have it so you can see the sequence occurring. Next up, we make it 2L periodic. I'm just redrawing the axes quickly. X-axis going from -15 to 15, so I have 3 full periods. So once again, we already had open circle at -5, 0, connecting to open circle at 0, 0. We have an open circle at 0, 2, connecting to open circle at 5, 2. And making this 2L periodic, we'll just copy that, shifting it over. So we'll have an open circle at 5, 0, connecting to an open circle at 10, 0. Then open circle at 10, 2, connecting to an open circle at 15, 2. Doing our shifting to the left, we would have open circle at -15, 0 to an open circle at -10, 0. Open circle at -10, 2, connecting to an open circle at -5, 2. Taking this whole thing then, doing our final step of adding in the points, splitting the difference in our jump discontinuities. We will put in a point at -10, 1. That's halfway between the 2 open circles at -10. We will put in a point at -5, 1. Again, that's halfway between the 2 open circles at -5. Put in a point at 0, 1, a point at 5, 1, a point at 10, 1, and then of course there are points also at 15, 1 and -15, 1 as our 2L or 10 periodic function would have. So this is what our Fourier series converges to. It looks almost like f, except it is turned into a 10 periodic function. And at the jump discontinuities, we split the difference. So this is our Fourier series. Of our original function f of x. Now, if we show this in decimals, we can see the series actually going to this. So I'm just going to switch over to decimals quickly. We can put in our original, what we found our Fourier series to be, and go from there. So again, recall that our Fourier series we found to be 1 plus the sum sum from n equals 1 to infinity, let's just start off with something. I'm actually just going to put in another letter and then we can increase it as we go. So let's go from n equals 1 to capital N of, we had 4 over, in parentheses, 2 times n minus 1 times pi. And then that was all multiplying sine of 2n minus 1 times pi divided by 5, and then times x. And I'm going to click on add slider for n. So this is just going up to 1. And here is just going out to 10 terms in that series. So as you can see, just going out to 10 terms in that series, we can already see more or less our pattern occurring. We can make our n go up to 100 if we wish. And now going all the way up to n equals 100, we can see now that we're even closer to what we were hoping to get. So this, we did get our series. Each of these are continuous until we go all the way up to n equals infinity, at which point we will get our jump discontinuities. But this is our Fourier series that we found going out through the 100th term. That's more or less the function we started with, again, turned into a 10 periodic function. In the next videos, we will see some shortcuts for finding Fourier series, specifically if we're working with either even or odd functions.